So this is joint work with Lucas Alieti, who is currently a postdoc at École Normale Supérieure, and Lenka, who's organizing this very nice school. So this is some theoretical contribution to the problem of pool-based active learning. So here's a quick recap for those of you who may be unfamiliar with it. So it's pretty convenient because it's really short to state. So imagine you have a huge data set which you want to train a neural network, which you want to use to train a neural network in a supervised fashion. But problem is, for whatever reason, you can't use it all. You have to select a fraction of that data set and only use that fraction to train your neural network. So this is not just theoretical wishful thinking, it happens in practice. So one setting which I find particularly telling where such limitation can be encountered is this paper by Zhang and collaborators. So those guys are doing physical chemistry and they want to train a machine learning algorithm to predict some interatomic potential in materials. So potentially the number of existing materials is really large, of course, but to get the label for one of those data points, you need to run a first principle ab initio calculation, which is really costly and lengthy, so you can't do it for any possibly existing material. So you have to choose at the beginning some data points, and only those data points will you label and hand them to your neural network for training. So of course, if not using the whole data set, you're throwing away some data points, you're losing information, and then the question is just how much are you losing? So we quantified that in this teacher-student perception learning, so which many talks defined before me, so quick refresher. So the data which we use is just Gaussian noise, white Gaussian noise, and then we generate the labels using a reference perceptron with weight vector x0, and then we try to fit a student perception on it. And everything I'll be telling you is in the limit where the number of samples p goes to infinity with the dimension n with fixed ratio alpha. So there, if you think about it, there are only two natural questions which you can actually ask. The first one is information theoretic. Just if I'm throwing away some data points because I can only use a fraction small n of my data set, I'm losing information, but what maximal information which I can save, which I can preserve by only using a fraction of my data set? So this gives us a high bound on the amount of information which you can preserve by only using a fraction of that data set. And once you have that high bound, the next most logical question is, can I design an algorithm that will tell me a smart way to select, to carry out that selection, so that, well, I'm close to that optimum amount of information. So a quick precision perhaps of what I mean by how we can measure the informativeness and the intelligence of a way to select stuff. So by information I mean the mutual information between the label and the teacher weight. So basically you want to select the subset S star, so that if I give you the label plus or minus 1 for the samples in S star, you can actually extract from it the maximal amount of information about the x0 which I used to generate those labels. And so you have a more precise idea of what the teacher is, and therefore your student will be able to better generalize. So it's the intuitive measure, I'd say, for the natural one, to measure if a subset is informative or is not. And it's all the more intuitive, I'd say, if you're a physicist, because you can play around a bit with this mutual information, and you realize it's nothing else but the free entropy, or minus the Gardner volume, or minus the version space. So it has really many names, but basically think of it as a proxy for the generalization error of the student. So, well, this volume just is a kind of entropy. Last technical slide, then there's no more equations, I promise. So the goal is to compute the complexity sigma n of v. So if you fix a fraction n, which I am allowed to use of the data set, say 30%, this is the logarithm of the number of ways which I have to select those 30% of the data set, so that at the end of the day I have an entropy v, or a Gardner volume v. Okay, so you set up a large division computations. If you're a physicist, you call this computing a grand canonical partition function with inverse temperature beta and chemical potential phi, then you do a Legendre transform. I will not detail this, and you use replicas to do it in a double replica symmetric assumption, one for the selection variables and one for the spin. So moving on to the results. So this are the results as I promised. The complexity sigma versus the entropy V. So I'll tell you a bit what there's to see in this figure. So basically here the pool is psi 3n, okay, p equals 3n. And basically if you take small n equals 0.3, it means that you are using 10% of your data set. And so as you can see from this, this corresponds to this rightmost curve. As you can see, there's lots of ways that I have to select this 10% so that I have a Gardner volume of 0.8. If I want smaller Gardner volume that is less entropy, that is more information, that is better generalization, I have to select this 10% in a smarter way. And of course, if there are less ways to do so, and that's why if you're asking for smaller V's, this complexity is decreasing. And it decreases all the way down to an entropy of 0.6, where there is only one single way of selecting those 10% from your pool of available data so that you have an entropy of 0.6. So in other words, it's the smartest way of selecting 10% of the data set. And this is the minimal achievable entropy which you can have. And you can repeat that analysis for 20% of the data set, 30%, etc. So this gives you a lower bound for the Gardner volume, or equivalently a higher bound of the amount of information which you can preserve by sacrificing a part of your data set. So far the discussion has been very hugely information theoretic. And you may wonder, are they far off? Can we design an algorithm that can approach this bounds? And the answer is yes. So we basically took AMP, we adapted it into an active learning algorithm. And the purple line is the lower bound which we derived for the Gardner volume. So this left plot is for the Gardner volume, and the right plot is for the generalization error. And the fact that they look pretty much the same just goes on to confirm that we were right in using V as a proxy for the generalization error. So the blue dotted line is our AMP procedure, and it's performing quite well. It's quite close to the best you can do. And we have designed a more, let's say, ignorant form of this very same algorithm, which is the yellow dotted lines, which we call agnostic ALAMP. So the difference between those two is the yellow has only access to the samples, while this one has also knowledge of the label. So you can use that knowledge, efficiently leverage on that to select things in a smarter way. That's why this blue one is performing better. And actually there is also a lower bound for this kind of agnostic strategies that exist in the literature. I put it with the reference here. It's a very classic piece of work. And last slide, actually. You may wonder what's the use of deriving those error bounds apart from it being interesting by itself. So one use we can think of is just to benchmark existing algorithms. You take heuristic strategies that were proposed in the literature that tell you a smart way to select a subset, and you can implement them in our setting and see how well they perform, how close they are from being just randomly selecting those samples, which corresponds to the blue curves, or how close they are from optimality, which is this dashed line here. And so while these are the results of some algorithm, you can find the details of what exactly they do in these references. But for example, this knowing the optimal bound here allows us to say, oh, well, this perception-based uncertainty sampling is not performing very well for small fractions, but then it gets optimal. So it gives you a really quantitative way of evaluating if an algorithm is good or bad. So as you may have realized, everything I've been telling you is really done for this particular data structure and this particular architecture. And well, you may wonder if this kind of benchmarking holds for different architecture or more structured data. And the question is, we don't know. So if you have any idea, you can try it. But basically, you'd have to repeat that computation to get the lower bound for the setting at hand. And then, as you may have seen, the AMP-inspired strategies that we use are performing pretty well, pretty close to the optimum in this case. But they are known to break down for more structured data, and real data is structured. So one possible way to continue this work is to adapt it so that it is more robust and can work as an active learning strategy for real-world data. And thank you for your attention.
Thank you. Do we have questions for Hugo?
Yes.
So the material scientist, you mentioned that one motivation was the material science, which one should you know? What do they do in practice, and how far are you from even giving them qualitative advice?
I'm very far. I'm really, really far.
I know I want to. Or can you already?
Well, basically, you get some insight, of course, about what data to select. I forgot which exact strategy they actually use in their paper, so I have to check.
Something close to the query by committee.
To the query by
based on
committee?
Uncertainty on the
Okay.
disagreement on the
Yeah.
parameters.
But basically, this kind of theoretical analysis can shed some light about what's the feature of the subset which you want. For example, it's quite logical that you want stuff that are orthogonal enough. And so this is just a way in a simple toy model to understand better. It's not practical yet.
Other questions? Then if not, let's meet the speakers. Thank you, Hugo.
Oh.
Great. So the next talk is by Leonardo on compressing invariant manifolds in neural nets.
Okay, thank you everybody for being here. So what we talk about is part of our work we did together with Mathieu, Mario, and others from our group. So the big picture, let's say, that motivates our work is the fact that the observation of neural networks adapt to the structure in the data, and in fact the success of neural networks is often attributed to the fact that they are learning features in the data. So, for example, if you take a deep network classifying images and we look at the hidden layers, people see that the layer, for example, act as edge detectors, and then as you go deeper, you find higher level features. So the interesting thing is that if a certain neuron, for example, spikes if it sees a face, then if you and you have a face in your input image, and then you deform a little bit your input image, or you translate it, you have that the neuron is still spiking. So these features have also learned to be invariant to transformation which are not affecting the classification task. And this is deeply related to at the same time compressing the features which are not relevant for the classification task. And for example, a very simple example about this, what compression could be is that if you take, for example, a Cypher10 data point, you could imagine that the pixels in the corner, they don't contribute to the label class, and so that you want to get rid of that information in the deeper layers. The one thing here is that there are many observations, intuitions, but there's been also some work, but there is no, let's say, general framework. I mean, this would be the long-term goal will be to have a general framework to understand these kind of aspects. Some observables have indeed been proposed to study these features, invariance, and compression. But I won't go into that. I just cite them is mutual information and effective dimension. So what I want to do here instead is to bring the discussion about the two different learning regimes, so the layer regime and the feature regime, into this context. And you already heard much about these two regimes in the lecture by Mathieu. So I just want to focus on one specific aspect here, which is the fact that the weights at the NTK. In one case, they are constant during learning, and in the other case, they evolve. So, if we go back to the fact that we want to, this idea that neural networks are learning features, we see that in one case we cannot learn features because the weights cannot change so the weights even in the deeper layers, they don't change. Whereas in the other case, we can possibly learn features and perform compression. So what we propose to do is to use this evolving NTK in the feature regime to understand, to diagnose compression at least. To do that, we focus on very simple models. And so we look at a classification task. And so we have data points X. And in these data points, we identify two. So if we have data points in a certain space, we identify two subspaces. One which we call the one in which X parallel lives, and the other one in which the so the perpendicular subspace in which X perpendicular lives. And this is done in such a way that the labeling function then depends only on the perpendicular subspace. So we studied different models which satisfy this constraint, let's say. And here what I propose you to look at is just to look at the simplest possible one, which is the one in which you only have one parallel direction. So X parallel is just let's say one, like the x-axis, like in this picture. So what you can have if you have if your leveling function depends only on one possible direction, what you can have is that so if you color like points so if you have two so you have two labels, you color your points. What you can have is just stripes of labels, plus or minus ones. And so this is one instance of this kind of data set. This is what we call the stripe model because it's just stripes of different labels. What we do is we train fully connected one in the layer neural network on this kind of data. So I just put like that's the form of the network we are training. So with all the scaling that Matteo told you about today. And we want to understand so we want to look at the evolution of the NTK. So the first thing we look at is the dynamics of the weights. So the dynamics of the training. So we look at what the weights are doing.
But sorry, do you use the NTK scaling or do you use the scaling?
So what we do here is we use the let's say the alpha trick to go from one to another regime.
Ah, okay.
So we have the NTK. So the NTK scaling will be the one with the square root of D inside, but then we have the 1 over H, which is the hydrodynamic.
Yeah, that's what I did. Okay.
But what we do is we put ourselves in so we are sure to be in the feature regime.
Ah, okay.
So and this you can, like if you look at the weights evolution, this you can say because on the background there is data set, on top is the orientation of the weights and they evolve.
Okay, I see. I was just confused by something.
Okay. Sorry, okay. So the training dynamics is an approximation of gradient flow. So we have a learning rate which is adaptive, and we try to take, so it's full batch gradient descent, and then we adapt the learning rate in order to follow gradient flow to some level. What we see, what we expect that if we can move the weights, what we want to do is to align with the only relevant direction, and this is what we see that it's happening in this context. And from this, we can tell something about the network function, first of all. So the network function loses the dependence on the parallel directions, perpendicular directions. And on top of that, the NTK evolves with the weights, and also the NTK loses the dependence on this perpendicular direction. Then in the next points, I'm going to make an argument which can be made more formal, but I will just, so I want to look at the eigenvectors now of the NTK, and I will just give an idea of what the argument is, but it can be found like in the preprint, or you can ask me if, this is a bit, and it could be, I don't know, precise. It can be made more precise. so we observe that, so we show that the NTK eigenvectors are of two kinds. So one kind is just dependent on the parallel components, and the other kind is a function of the parallel components, a linear function of the perpendicular ones. And so given that the labeling function only depends on the parallel components, we expect some of these eigenvectors to, at the end of training, to be more informative about the label of the points. And we also expect the projection on this label to be large. So for kernel method, it is known that if this projection on the top eigenvector is large, one expects good performance. So if you use if the projection of this of the top eigenvectors at the end of training on the label function is large, you expect to have a good performance when you use your kernel, your NTK, for a kernel method. But so more on that will be on also set of Matthias' lecture.
Can I just ask some more details on the model? Like, so now you have a one-dimensional space X parallel. So
Yes.
what's the dimension of the X perpendicular?
So in this specific picture, I think it's just 2, so it's just what you see. But then we did with 5, so
So it's low-dimensional overall, actually.
it's low-dimensional overall. So the main experiments we have also in the preprint is with dimension 5 and 10. And you see, so if you project, I mean, if you plot only the relevant dimension and one of the other ones, you see this. So we have some predictions on the what these eigenvectors should be with respect to the labeling function. So we can test this prediction via kernel PCA. So of course we cannot access. So we can guess the form of the eigenfunction, but we cannot access them directly. What we can do is we can compute the ground matrix of the neural tangent kernel, and then we can perform PCA on this matrix. So the principal components of this matrix will be an approximation of the eigenvectors of the NTK. So what is plotted here, so on the x-axis what we have is the index of the eigenvectors starting from the 1 corresponding to the largest eigenvalues, and and then you go in descending order. And then on the y-axis we have on the left plot the mutual information, so an estimation of the mutual information between the eigenvector and the label, and on the right we have the projection of the eigenvector on the label. So what we see here is that if we look at the blue bars, so this is the eigenvectors for the NTK before learning, they have they share no information with the label, and the projection is very small. Whereas if you look at the orange bars, which is the correspond to the NTK at the end of training, we see that, especially for the top eigenvector, we see that the shared information is very large, and also the projection is very large. So this is the two things we observe and we verify as we expected. So the last point of the argument was that this large projection would imply an improved NTK performance if used in a kernel method. So, by performance, or by performance, I mean test error, of course. So what we look at now is what is called learning curve. So just to specify what's in the axis, we look at the plot of the test error as a function of the train set size. So we look at this when training the neural tangent when training a kernel method on the neural tangent kernel initialization, when training the network, and when training a kernel method with the NTK after training. So we see that the curve for the NTK initialization is the highest one, so it reaches a higher test error than the other two, and so the network performs better in this case. So it reaches lower test errors overall, and the curve has a larger slope. But the thing we were interested in is the performance. So
just like k nearest neighbors feature? Because this is very low dimension.
Yep.
And is k nearest neighbors learning features? I would say no, right? That's like
No.
the realest possible kernel you can think of.
Yeah.
But like I don't really see how in such a low dimensional setting like something can considerably improve on k nearest neighbors. So it would be interesting to add that.
So I guess that still, like you have a sharp interface, so it could be that you make mistakes with k-nearest neighbors around there.
But what's the dimension? 10?
What we use is 5 and 10, yes.
Yeah, it's very small. Oh, this is a this.
Okay, we'll look into that. But I won't expect it to perform. I would expect it to perform at the red curve. So this kernel is like kind of a Laplace. It does a Laplace cusp. So
That would be pretty.
okay, yes. Thanks for that. So so the observation so I wanted to point out at in this slide is that the kernel at the end of, so if we train the network, we compute the NTK and then we train on a new dataset using a kernel method, the performance of the NTK at the end of training is as good as the one of the network and much better than the one at initialization. So so we did this for simple data, so for our toy model. We looked also at empirical data, so we look at MNIST, and probably I don't have time to comment specifically on each plot, but as you can, if you have a glance at the plots, you can see something very similar to what we've seen in the stripe model. So okay, the first eigenvectors become very informative, and then here if you look at the curves, so sorry, we have different colors, but the initialization, we have this curve here for the indicated initialization, and then we have two curves here which are almost the same for the network and the indicated at the end of training. So I have 30 more seconds. Okay, I just say that so we can look at so we can plot in fact these eigenvectors just to look at the so what we have in this plot is the scatter plot of the first two eigenvectors, and the points are colored depending on the label. And so this was just to connect with the fact that they have a high projection with the label. We have that in the first column we have the kernel initialization for the stripe and MNIST, and we see that there is no structure depending on the label in the.
Questo proprio non l'ho capito.
Sorry for that. What's happening? Okay. Then at the end of training we have structure, and then we have that the first and the second eigenvectors become informative. So I go to the conclusion. So we introduce a simple model to study compression in the feature learning regime. We've seen that compression shapes the NTK and makes it more performant. We've seen that kernel PCA can be used as a diagnostic for compression, and we pointed out that similarities between MNIST and the stripe model. So that and this fact supports the fact that compression could be relevant in MNIST as well. Thanks.
Any other questions? And just like we spoke with the compression at the beginning, but in the middle there was not much of it. So what do you mean by compression? Do you mean like that there are just few eigenvalues that are big and the others are small? Or what is really the compression in here?
So it could be so the fact that because okay, so the one paper that talks about compression is the THB1, but then we know that that there is some sketch. I mean, it's mutual information in that context wasn't the right thing to look at, but from that and also one similarity with this is that also here we have that so you get rid of information about the direction which is not relevant. So you only focus on the direction which is relevant. In this sense, you compress.
Or how the kernel evolves, basically. That's what you mean.
I'm sorry?
By how the kernel evolves.
Yes.
Can you teach me the trick if you're going to check? Are there one more question? Oh, perfect. Can we
Thank you.
All right, does it work? Yeah.
Okay, and so the last talk of today is by Michiel on dynamics of online learning and two-layer neural networks in the presence of concept.
Yeah, thank you, Lenka, and also for the organization of this very nice workshop. I will be presenting part of a larger work that we did with, it's a joint work, and you can check it out if you are interested. In this larger work, we also study learning vector quantization under concept drift, but here we'll mainly talk about neural networks under concept drift. So first I will quickly introduce what is concept drift, and then I will show the model scenario that we consider, which is the student-teacher setup that was already covered a lot here. And then I will show how we include concept drift in that model. And then last I will show results for the value soft committee machine and the error function soft committee machines. And I will emphasize the similarities of the behavior and the differences. So basically, traditionally, the assumption of stationarity in machine learning, that you have a training set of historical data on which you train your machine learning model, and you have an estimate on the test sets on how good it is going to perform, is often violated because the environment that the model operates on is non-stationary. So you can have a changing relation of the input-output relation. So here in a classification problem, the classification boundary really changes, or the model can get presented with different density of inputs than it saw in the training data. And so you need some way to account for that. So we model this in the student-teacher setup. So this has already been introduced, but teacher is a model that gives for all possible input the correct output. This is a regression problem. So the teacher is a soft committee machine of which the output is simply the sum of the hidden units, and we call the weight vectors P. And the student is the model that learns from the data. We can represent the scenario with a few macroscopic order parameters. So we have the student-student overlaps, which are the overlaps of the student weight vectors. The student-teacher overlaps R, and the teacher-teacher overlaps T, which we fix to orthonormal teachers. So we consider online learning here. So the student learns from a stream of random IID examples that are drawn in Rn, and the teacher gives the correct output for these examples. This has already been covered this morning. In this case, the pre-activations, or the local field, if you wish, of the students and teachers, they are Gaussian by the central limit theorem, and the second moment of the joint distributions are given by the values of the order parameters. So the student updates on every presentation here, and it updates with gradient descent. So we have an update rule for the student weight vectors, and we can then also directly formulate recursions of the order parameters. And in the limit n to infinity, actually these a quantity self-average. So one can so these equations become deterministic, and one can take the average over the joint probability of the pre-activations of the student and teacher. So this has been done by Saad and Sola in '95, and they used the error function, so sigmoidal activation, and several authors have also worked on this system for value activation. And this particular average contains four-dimensional averages, which are difficult to find in closed form for the value. So I also discussed with Sebastian, he has also looked at this, and it's quite difficult. So like I said, we consider the limit n to infinity, and for this reason that we don't have closed form averages for this, we consider also the limit of small learning rates. And if we rescale the time variable by the learning rate and 1 over n, this basically becomes continuous in these limits, and we can write differential equations. So at each step, we assume that the teacher vectors drifts randomly, and the quantity delta determines the strength of this drift, basically, this random drift, and we also introduce wave decay in the student. The gamma determines the strength of the shrinkage, basically. And we model those two effects in the differential equations. And we also, the quantity that we are interested in is, of course, the generalization error, which is the expected value of the square deviation. And we take the average over the joint distribution of pre-activations, and we get closed form expressions in the order parameters for both the value and for the Earth system, which Saad and Sola already did. So now we solve that system for increasing amounts of concept drift for both SCM, and we start from initial conditions that reflect a random initialization of the student with respect to the teacher of the student. So the student-teacher overlaps will be more or less 0. And here you see for increasing amounts of concept drift how this system behaves. So typically in the beginning you have a sharp increase of the student-teacher overlaps. In this phase the student basically approximates the rule, and basically these values plateau, and actually this is a fixed point of the dynamics, which is repulsive, and eventually the student units start to specialize into the teacher unit, and it loses the specialization to the other unit. So here I show the evolution of the generalization error, which then decreases sharply in the beginning, plateaus, and with specialization decreases to 0 in the case of 0 concept drift. With dots I show simulations that we did for finite n, of course, n is 500. So yeah, what you can observe is with increasing concept drifts, the plateau length increases as well as the performance decreases. Here we show that the generalization error that is achieved in the unspecialized plateau state and in the final state as a function of increasing concept drift. And for both SCM there is a point, there's a critical delta at which specialization is not possible anymore. So the student stays in the state where it approximates the drifting teacher. And here we show how the plateau length increases with the strength of the concept drift, which for both SCM diverge up to this value delta C. What we saw for the behavior if one introduces wave decay is quite different for the two SCM. So for both SCM, introducing a small value of wave decay can improve the final generalization error potentially, but the Earth SCM system quickly loses its ability to specialize, which is not the case for the Rayleigh SCM. It's more robust to the setting of the wave decay. But I think what's more interesting is that in the Earth SCM, introducing a wave decay always increases the plateau length, while it significantly reduces the plateau length for even optimal values of wave decay. And here we show, here we show basically a measure of specialization, which is R minus S, and R is the specialization of a unit to a teacher unit minus the specialization it still has with the other unit. And what we have done here is we have looked for increasing value of the concept drift. We have searched for optimal values of weight decay, which optimizes this quantity. And for the ERV-SVM, you can see that it never optimizes the specialization. And it can also, weight decay can also not introduce specialization after this critical delta. But for the ReLU-SVM, actually this R minus S is improved by the weight decay. And also after the critical delta, at which specialization was not possible without weight decay, for larger delta, specialization is possible. So by suppressing the gradients of the older examples, which are less representative of the rule, the system can still specialize. So we have seen the similarities and how the systems react to this type of random drift, and the differences, which are mainly in the weight decay effect. So weight decay really increases specialization for the ReLU-SVM, and it reduces also the plateau length that is necessary to achieve specialization. And this is not the case with the error function SVM. So this is a simple first scenario that we studied in this work. But in the future, we would like to study also other types of real drift in the teacher. So when student and teacher, when teacher factors align, for example, making the rule less complex, or de-align, make them more complex. But also we would like to study virtual drift by changing the density of inputs. And I think the hidden manifold model is potentially a good candidate for that. Also, we would like to study more advanced architectures and also mismatch student and teacher. Also differ the activation function of student and teacher to make this scenario more comparable. And yeah, of course, we're also looking at deeper neural networks in this scenario. We started with 3 architectures. But that's for the future. So.
Okay, thank you. Do we have questions for Miguel? At the view. So thanks to all the speakers of this afternoon.